Hello and welcome to the Quant Methods portion of the Level 2 video series. If you're watching this straight through, you just finished the ethics sometime in your study efforts and you were hoping to see somebody else when you flipped on the Quant Methods, but here I am back to work with you again. My name's Andrew Holmes. I'm a professor at Brigham Young University, and I am a frequent contributor to Kaplan Schweizer's instructional team. So happy to be here, happy to go through this quant method stuff with you. I think this is a really great treatment. It is incremental. It starts out slow, works up through the intricacies of regression, then multiple regression, and on into time series stuff. So I think there's a lot that we can learn here, and I think that this is a fairly effective study area. So in other words, when you look out at where you can spend a few hours and pick up some points on the exam, if your quant methods skills are rusty, or if you really haven't been forced through this stuff previously or been a long time, whatever, I think you'll find that this is something you can get on top of. One of the reasons I like this is because I think it is fairly well contained. And what I mean by that is what you see in the quant methods in your Schweizer notes or here on the video is going to look a lot like what you're going to see on the exam. There's not a whole lot of improvisation that you can do. There's not a lot of extension and those types of things. So I do believe that this is an effective study area, one that is relatively low on the tree, low-hanging fruit, as it were. So how are we going to progress through this? Well, we're going to have several readings here, but the main part of the progression is going to start here. We're going to talk about this topic summary on correlation and regression. Certainly regression is the big thing in this particular reading. However, what we'll see here is called simple linear regression, which means that we're only going to have one independent variable. If you don't know what that means, we'll explain in just a moment. What we're going to see in the next topic area, provided that you still have the stomach for that as you progress through the video series, is we're going to move on to multiple regression where we have multiple independent variables. So the things that we learn here in this reading about regression are going to carry forward to the next topic summary in a very direct fashion. We're just going to be expanding our understanding of regression. What we'll see as we go through this is there's going to be a number of times that I tell you, okay, here's the principle, here's how it works, but don't memorize this because we'll have a more general statement of it in the multiple regression topic summary. I do believe that multiple regression is the workhorse of the discipline. Also, if I had to pick one reading out of the quant methods material that I said was going to account for a big portion of the points or more points than the other readings, it would be the second topic summary in this area, that is multiple regression. But that's not to say that you can ignore time series, which comes later. So there's plenty of material to go around here. You don't have to worry about being bored because you don't have things to study. So let's jump right in. We'll talk first about correlation. So what we see here is a scatter diagram. So we're looking in the standard coordinate plane. Here we're looking at the return on an individual stock against the return on a market. On the market, that of course is the classic, the finance comparison, because what we're going to do eventually is take this, run a regression on it, and estimate this will be the way we estimate beta. So when we estimate the systematic risk of a stock, if you don't know what beta is yet, well, you probably ought to go back and review your level 1 stuff. So beta out of the capital asset pricing model, measure of systematic risk. Well, when you look at the dots here, what do you notice? Well, you probably notice that the dots are dominated in this quadrant and in this quadrant, right? So if we wanted to draw a line through the dots, we'd probably get something like that. That's actually what a regression equation does. It just finds the line of best fit. But the point here is what we see is that when we're increasing in this dimension, that is the return on the market's going up, we also see that we're increasing in this vertical dimension, that is the return on the stock. So what we would say is that this is positive correlation. So we see positive correlation here, but it's not perfect correlation. It's imperfect positive, which means that it's 0.9 or 0.8, something like that. Here we're going to say it's 0.9, which means that the two variables tend to move together. This doesn't imply causality, but they move together. So when one's up, the other's up, return on the market's up, return on the stock's up, and the vice versa if the return on the stock is down. If we saw negative correlation, we would see the dots running in this direction. Okay, so that would tell us that as the return on the market increased, the return on the stock fell. We do have negative beta stocks out there. Not that beta is the only thing we can do with regression. In fact, Regression is one of the most used statistical tools in the world. So, but we would see the association running the opposite direction. And of course, if we saw the association looking like this, where we got a straight flat line, okay, well then we'd see as the market increased or the market decreased, it didn't impact the return on the stock, and we would say that is a correlation of 0. So we don't have any recognizable relationship between those two variables, at least in a linear sense. All right, so we have a couple of concepts here. We talked about covariance at level 1, and we talked about how that was an absolute measure of how two variables move together. So that can be the return on one stock, the return on another stock. It could be yak milk production and sunspots. It could be any two things. The point here is that it's an absolute measure, which means that it is essentially bounded between, in this case, between minus infinity and positive infinity, and it's difficult to interpret. So if you tell me the covariance is 47, well, I don't know what that means, other than there tended to be less strong positive co-movement than if the covariance had been 48. So interpretation of covariance is very difficult. However, we can take covariance and we can morph it into correlation. Correlation is a standardized or unitless measure that's bounded between -1 and +1. So if we have a +1 correlation, that's perfect positive correlation. The variables are moving together in lockstep so when one's up, the other's up, one's down, the other's down. 0 correlation means that there's no linear association, and negative correlation, that is correlation between -1 and 0, means the variables are moving in the opposite direction. So we can have positive correlation all the way up to perfect positive, and negative correlation all the way down to perfect negative. To see what we're looking at, well, here we see that this is all the dots are falling on this straight line, so that's perfect positive correlation. Here the association is negative, but notice that it's not perfect. So this is imperfect negative, this is perfect negative, this is imperfect positive. Here, if we drew a line, we'd see that we got a flat line, a trend line through that, so there's 0 correlation. Now, the thing that you really need to learn from this slide is that if we wanted to draw a characteristic line on this last graph, we would also get something that looks like this. Okay, so in other words, we get a correlation coefficient of 0, even though clearly these two variables, x and y, are related. It's just that the relation is in a nonlinear fashion, and correlation is a linear measure of linear association. That's what I was trying to spit out. Now, how do we calculate covariance? This is something that I would be surprised to see on a level 2 exam, calculation of covariance from raw data. But remember, when we calculated variance, we took the return in each state of the world minus its expected or mean return, and then we squared that, right? And then we summed up and divided by n minus 1. Well, here, rather than square, these of course are both to the first power, what we're doing is taking the first variable that we're looking at association for, subtracting off its mean, the second variable that we're looking at in this state of the world minus its mean. So for this particular state of the world, if this is positive and this is positive, then we are going to get a positive number in the numerator. Okay? Likewise, if the variables are below their mean, that is, this is negative and this is negative, then we are going to get a positive number again. So if they're moving up together above their respective means or down together below their respective means, then we get a positive number. It's only when one is above and one is below that we will get some negative number in the numerator. Well, if that happens often enough, of course, the overall covariance will turn out to be negative. So looking at some quick calculations, we have stocks 1 and 2. You see that we have 3 years here. So for stock 1, it's 5% minus 2 and plus 12%. For stock 2, it's 7% minus 4 and 18%. We can calculate the covariance on that. Of course, what we'd have to do first is calculate the means. So we could take the means of stock 1, we're given here on the slide, is 5%. Stock 2 is 7%. Now, notice that the observations in year 1 are 5 and 7. That just means that we've strategically planned this example so that we can minimize the arithmetic. But nonetheless, we're going to take the outcome in the first year minus its average. So in the first year we had 5%. We're going to subtract off the 5% average for stock 1, the 7% outcome for stock 2 minus its average of 7%. So we get 0 times 0 here as the summation of, or the product of the differences. Okay, then we do the same thing for year 2. We're going to take minus 2 minus 5, which of course is minus 7 over here, and then we're going to take minus 4 minus 7, which is minus 11, so we'll take minus 7 times minus 11, and we get this. Okay, we'll do the same thing for 3, sum up, divide by n minus 1. So this is, of course, a sample, so we're using n minus 1 and not n, and we end up with a covariance of 0.0077. And what's the problem with that? Well, the problem, of course, is that it's hard to interpret. So how can we take that and convert it into correlation, which is easy to interpret and is the foundational principle for most of it's the foundational principle for portfolio theory. So anyway, so here is a formula I would definitely put on my formula sheet. So when I did this, I kept 2 formula sheets, a primary and a secondary. Primary is one that I thought came up a lot when I was doing practice exams, or it had lots of fingers. It reached out and touched other concepts. Secondary were things that I thought if they showed up on the exam, they'd only show up for one question, but I'd like to know it if that question showed up, sort of a lower probability assessment. Well, this is certainly a primary formula sheet formula, so I'm going to put FS1 here so that this is something you want to know. So what this says is the correlation coefficient is equal to the covariance, which we calculated on the last slide, different numbers, different example, but divided by the product of the standard deviation. So correlation, if the correlation coefficient is 0.0051, standard deviation of 1 is 7, standard deviation of 2 is 11, we put all that in, what do we get? We get a correlation of 0.662. Notice that that's greater than 0, so what we have here is imperfect positive correlation. I think that this formula for correlation from covariance is an important formula. The formula for calculating covariance from basic data, I would assign a lower probability to, just because it's all arithmetic and it takes a lot of time to calculate, and this is a timed exam, and they've got to make give some nod to reasonableness in terms of how many calculations you have to make. So anyway, correlation bounded by minus 1 and positive 1. It's a standardized measure. Greater than 0, positive correlation. Less than 0, negative correlation. What about the limits to our correlation analysis? Well, we do have some limitations. First of all, we're looking at the possibility of outliers. What we mean by outliers, if we draw a quick graph here, is when we're looking at the coordinate plane, and then we take our data, we put it on here, and it looks like this. So there's all our data. Well, if we have an outlier, you can see the data is bunched up in this general area. What if we have a variable up here? Okay. Well, that's an outlier from the rest of the data, but what you would see is that that wouldn't have much impact on the correlation because it tends to lie close to the trend line. Okay. On the other hand, okay, if we had an outlier that was up here, so it's a long way from the data, so here would be the trend line without it, what we would see is that that one observation, okay, would change the trend line fairly dramatically to something like that. So we've got to decide whether or not this outlier should be included in our data set, and that's going to be a determination of whether this was something that was random, whether it's something that's likely to reoccur, and if it is, then we probably want to leave it in. Okay, spurious correlation, this is the idea that we identify a linear relationship, but there's no economic explanation. So, that's going to be, well, for outliers, you can think of the market crash in October of '87. Spurious correlation, you can think of the correlation between who wins the Super Bowl and the S&P 500. So I forget which way this runs. I think it's if the NFC team wins, then the S&P 500 goes up that year. Well, of course, there's no causal relationship between who wins the Super Bowl and returns on the stock market. So this is what we would call spurious correlation. It's not likely to be borne out in the future. And finally, nonlinear. We already looked at a picture of this. If we had nonlinear association, we wouldn't be able to pick that up with correlation, and that would be something like the relationship between market capitalization and return. So small cap firms have higher returns than large cap firms, but that relationship is not linear. Now, the question's going to come up a number of times when we look at these parameters that we're estimating, or these sample statistics. Are they significant, or are they significantly different from some hypothesized value? This gets back to the hypothesis testing stuff that you saw at level 1. So this is nothing but a t-test. So remember we had z-tests and t-tests. What you're going to see primarily here at level 2 are going to be t-tests. As a quick refresher on the t-test, in case you haven't been using that much since you took the level 1 exam, what we're doing here is we're taking and we're assuming that the variable that we are estimating, so we're estimating some sort of random variable, lies along some distribution. And there's a good reason for it to look this way. And we're going to come up with a hypothesis test. Basically, we're going to have a null hypothesis that the correlation is equal to something. In this case, the formula is very specific. This is a test for whether or not the correlation is equal to 0. So we're going to put H naught, or the null hypothesis, at the center of this distribution. And then the t statistic is basically allowing us to calculate either how many standard deviations or how many standard errors we are away from this null hypothesis. So if the actual observation that we look at is here, or it's here, well, it's not exactly equal to 0, but it's awfully close. So can we conclude that the true correlation, remember, this is a hypothesis test, and we're trying to infer something about truth, but we can never observe truth in the statistical sense. So we're looking at this and we're saying, well, is it possible that the true correlation is actually equal to 0, or is it likely that the true correlation could be equal to 0? And if we end up close to this, we're saying, yeah, that's not enough evidence to reject the notion that the correlation is equal to 0. But if we go back and we find that our observation, the correlation that we have calculated, is actually way up here, something like, let's call it 3 standard deviations or 3 standard errors away from this hypothesized value, then we're going to say, there's only a little bit of space out here in the tails. These are tails of a normal distribution, so remember they go on forever. But we're saying, the odds that we are going to observe something way out here when the truth is described by the null hypothesis, that seems to be small. So what we're going to do is reject the null hypothesis and accept the alternative hypothesis. So we're going to have something like this that's going to be, something about +2 standard errors, standard deviations, to -2 standard errors, standard deviations. That if we're dealing with not the student t, but with the z distribution, that would be 1.96 to -1.96. Well, in this range, this is going to be our fail to reject range. Right? So we're going to fail to reject if our test statistic ends up in this range. If we're out here in the tails, then we're going to conclude that it is unlikely that the true value of the parameter is equal to the null value, and we're going to reject the null value and accept the alternative. So that's a quick refresher course on what's going on with hypothesis testing. If it's been a while since you looked at that, remember, you don't accept the null hypothesis. All you can do is fail to reject the null hypothesis. Why? Because we set the test up to make it look like the null hypothesis was true. We put that at the center of this distribution. So we can fail to reject, or we can reject the null hypothesis. And we're really not proving anything. All we're doing if we reject the null hypothesis is saying that the evidence leans to the idea that the null hypothesis is not true. So this is a formula that I would put on my formula sheet. I would probably put it on my secondary formula sheet. It's distributed with n-2 degrees of freedom, which just means that when we look up the t-statistic in the table, we've got to allow for 2 degrees of freedom there, or n-2 degrees of freedom. So remember, the normal distribution is the same as the t-distribution with infinite degrees of freedom. So it's going to say that what we're doing with the t-distribution is we're taking our confidence interval and we're making it a little wider. So we're moving it out just a little bit. You can think of this as a more conservative way to do hypothesis testing. All right, and that is our treatment of correlation. Now we're ready to move on to linear regression. So we're going to start with simple linear regression. That's where we're going to have one variable, the dependent variable, that we are trying to explain, and another variable, the independent variable. This is the one that we're going to use to explain the variation in the dependent variable. Okay, so suppose we want to predict housing starts as a function of interest rates. Well, then interest rates are going to be the independent variable. Housing starts are going to be the dependent variable. We're looking at changes in interest rates and how that impacts housing starts. Important to realize that the mathematics of this do not identify causality. So is it housing starts that impact interest rates or interest rates that impact housing starts? Okay, we have to use economic logic to determine the flow of causality. But at the end of the day, for all our talk about regression analysis, okay, if you go back and you think to your 7th or 8th grade pre-algebra teacher, it was Mrs. Somebody. Who was that? Okay? For me, it was Miss Robinson. Okay? And she tortured you all semester long or all year long with this formula that was y is equal to mx plus b. Well, here's y, here's b, and here is mx. So we're using a beta 1 instead of an m. But this is just a formula for a straight line. This little epsilon on the end is just reminding us that we're estimating this relationship with error, so all the dots won't fall right on the line. But all we're doing here, the point of that is all we do with regression analysis, whether it's simple linear here, that is when we have one independent variable, or in the next reading when we have multiple independent variables, all we're doing is estimating a straight line. Okay? So in this case, the y variable would be called the dependent variable. That's what we are trying to understand. Okay? We're going to estimate that as a function of an intercept. Okay? Here's the slope coefficient. Here is the independent variable. In our initial treatment of regression analysis, and that's all we really are going to get in the CFA curriculum, the variable of interest is usually this beta 1. It's the slope coefficient on the independent variable. So if that is equal to 0, what does that mean? Well, how does y change when x changes? Well, x doesn't impact y. The slope coefficient is equal to 0. So, we could test it relative to anything, but what we're going to frequently be interested in is this significantly different from 0, and is it positive or negative? If it's positive, that tells us that as x increases, y tends to increase, and if it's negative, as x increases, y tends to decrease. But at the end of the day, like I said, this is nothing more than the estimation of a straight line. Okay, what about the assumptions of the linear regression model? Okay, well, the big one is we assume that there is a relationship between the independent linear relationship between the independent and dependent variable. Okay, this is the hard one, and we don't have any good mathematics to go behind that, so we're going to look behind that one. So for the most part, we're going to ignore it. Okay, the independent variable is uncorrelated with the error term. The expected value of the error term is 0. The variance of the error term is constant. The error term is independently distributed, and the error term is normally distributed. So it's independently distributed and normally distributed. Okay, those are all assumptions of the linear regression model. Do you need to memorize these? Well, good news and bad news. Okay, the good news is you don't need to memorize this list. And the bad news is the reason you're not going to memorize this list is because there's a better list, meaning that it's a little bit longer in the next topic summary that we will get to. That provides the list you really ought to work to. So we'll see the assumptions. We're going to add another assumption down here that's going to be important for us, and then that's the list I would actually commit to memory. Somewhat unfortunately, in my estimation, lists are important on the exam from time to time. So asking which of these is an assumption of the linear regression model, while I personally don't think that's a great question, it wouldn't surprise me to see that show up on the exam. All right, so what does all this look like? Well, if we took away this this straight red line in the middle, and all you saw was these black dots, okay, well, that would look like the very first slide we saw in this topic summary. That is, it's a scatter diagram. All the regression equation is going to do is it's going to find the line of best fit, okay, the one that goes through the middle of the dots, if you want to think of it that way. Okay, the way it actually works is it minimizes the vertical distance between all the given observations and the line. So it calculates that distance and it minimizes it. What it actually does is minimize the sum of the square differences, but I don't think the square builds a lot of intuition. So just think of it as absolute value or something. Anyway, so it's minimizing the sum of the differences between the vertical distances between each dot and the line. Okay, and what we're normally interested in is the slope. Okay, so the slope, of course, is just, the rise over the run, going back to Miss Robinson's class, right? Okay, we'll also get a y-intercept, which is going to be important from time to time. But what this says, the slope coefficient says that if the return on the market, if the return on the market is 10%, then the return on the stock is going to be 9%. Or if the return on the market is 1%, then the return on the stock should be 0.9 plus the 5%, plus the 5%, I'm trying to get rid of that line. There we go. The 5% intercept, right? So anyway, so I'm not sure that this line is drawn perfectly, but you get the idea. It's the slope coefficient, which is describing the relationship between the return on the market and the return on the stock. That is most important. We're going to use this equation some, so don't forget that one. The return on the stock is equal to 0.5% plus 0.9 times the return on the market, and that is 0.5%. I was interpreting it as 5% just a moment ago. Anyway, so we're going to use that equation to do some things later on. We call that the regression equation, or the estimated equation, or the estimated regression equation. So what is this telling us? Let's think about interpretation. So if we're thinking of the intercept, the 0.5%, that's the predicted value for the dependent variable if the independent variable was equal to 0. So what's the return on the stock going to be if the return on the market is 0? Well, the predicted return on the stock is going to be 0.5% when the independent variable takes on a value of 0. What about a change in the dependent variable for a 1-unit change in the independent variable? What this is telling us is that the return on the market goes up by 1%, then we would expect a change of 0.9% times this 1% for the change in the stock. This, by the way, is also how we estimate the beta that we use so much in the capital asset pricing model, which is, in my thought, the most used formula on the exam. If you don't remember the CAPM from level 1, then don't worry about that, because we're going to see it in a couple of different contexts here in the level 2 curriculum. All right, so now what are we going to be interested in? So if we go back and we look at that regression equation, the return on the stock is equal to 0.5% plus 0.9 times the return on the market. Okay, well, the immediate question we would ask ourselves is this slope coefficient significantly different from 0? Because if it's not significantly different from 0, what it would say is that, well, the return on the market and the return on the stock don't appear to be related in a statistically significant way. So what we can do is we can use our t-test, the same thing we talked about previously with the significance of the correlation coefficient. We can do another type of t-test in order to test the significance of the slope coefficient. And this is going to be something we're going to see over and over as we go through this reading and the next reading and the time series reading. So this is something you definitely want to have down, although I'm going to tell you not to memorize this in just a moment. Anyway, this is just a t-test distributed with n-2 degrees of freedom. So here is the basic formula for the t-test here. We're going to take the estimated coefficient and subtract off the hypothesized value and divide it by the standard error. We'll be given the standard error, we'll be given the estimate, and we'll be given the hypothesized value on the exam. Okay, the estimate and the standard error are standard output from a regression statistical package. So what if we wanted, so in this hypothesized value could be anything. We could test that slope coefficient of 0.9 and say, well, is it different from 0.23? Okay, if there was some reason that we wanted to know that, we would be fine doing that just as you see here. However, we frequently want to test what is called the statistical significance, which means we want to test this versus the null hypothesis that the coefficient is equal to 0. So we want to know if the coefficient is equal to 0, which means the hypothesized value is going to be 0. So the very frequent test statistic we see for the slope coefficient in a regression equation is the estimated slope minus 0 over the standard error, and that's going to come out to some value. You know, it could be anywhere from, well, it could be anywhere from 0 to infinity, but what we're really looking for is something that is, you know, if it's greater than 2-ish, okay, then that's going to indicate that the coefficient is statistically different from 0. So depending on sample size, depending on the degrees of freedom, n, remember, is the number of observations in our sample, so n-2 degrees of freedom. Getting rid of this junk. So let's see. So there's one other note here, and that is to remember not to you don't need to memorize the formulas you see here. Once again, it's because we're going to see a more general version in the next reading. All we're really going to change is this statement of degrees of freedom. This is going to look exactly the same, but since what we'll see in the next reading works for that reading and this reading, no reason to write it down twice, right? So you don't want to have two formulas when one formula will do. Let's do some testing with this and see if we can use it. All right, so looking at this, that we're going to test the statistical significance of the slope coefficient from the stock return regression at a 5% significance level. So recall that the researcher gets to determine the significance level. Here we're at the 5% alpha or 95% confidence level. We're going to assume that the standard error is 0.17, and of course we've already seen the slope coefficient of 0.9. Our null hypothesis is that the slope coefficient is equal to 0. We're testing that versus the alternative that it's not equal to 0. So we're going to calculate our t-stat. That's going to be the estimated coefficient divided by the standard error. It equals 5.3. The critical value, if we went to the t-tables and looked it up, is 2.2. So you learned how to do that at level 1. So, sorry, it's a little hot in here today. But anyway, so you learned how to do that at level 1. But remember, in this case, we're looking at a two-tailed test at 5% level. We're putting 2.5% in the upper tail, 2.5% in the lower tail. The degrees of freedom are going to be 10 because there's 12 observations here. So what we get, if we looked at the picture, which I think we have a picture of it, okay, is we're going to go from plus 2.2 to minus 2.2 in that range because that's our critical t-value. That comes from the table. If the estimated t-stat or if the calculated t-stat is between those bounds, minus 2.2 to plus 2.2, then we're going to fail to reject. We're not going to be able to conclude that the coefficient is significantly different from 0. But what do we get? We get an observation that's way the heck out here in the tail. It says we are 5.3 standard errors away from 0. So you've heard of the book 6 sigma. Okay, that's being 6 sigmas away from the middle. Well, we're 5.3 sigmas away from the middle. That's heckin' gone from the center of the distribution. So we're way out here. Even if we were at the 99% or the 99.9% level, we'd still probably be able to reject the null hypothesis. So in this case, since we are in the reject region, that is outside the minus 2.2 to plus 2.2, we are going to reject HO and conclude that the slope coefficient is significantly different from 0. Now, we can also take this point estimate of 0.9 and look at it in a different way. So we could form a confidence interval. Now, there's going to be 2 or 3 different kinds of confidence intervals that we're going to form as we go through the quant methods material. Don't lose sight of the fact that they're all calculated the same way. That's going to be some point estimate, some number that we've estimated, an estimated random variable, plus and minus a quantity that's going to be based on 2 measures. A reliability measure, which is frequently going to be a t-stat, okay, and then a variability measure, which is going to be a standard error or standard deviation, some measure of how volatile the underlying process is. So if we wanted to calculate a 95% confidence interval for this particular B1, we would take the estimated coefficient and then add and subtract from it a quantity equal to 2.2, that's our reliability coefficient from the t-tables, times 0.17, which is our variability coefficient, that is the standard error, and what we would get is the confidence interval is from 0.53 to 1.27. What does that mean? Okay, well, what that's telling us is that if we are testing whether or not this estimated random variable, 0.9, is different, statistically different from some value, at the 95% confidence level, is statistically different from some value that would be less than 0.53 or greater than 1.27, we're going to be able to reject the null hypothesis. But what if we wanted to know if 0.9 was different than, let's say, just for argument's sake, 0.6? Well, in that case, at the 95% level, we would not be able to reject. Why? Because 0.6 is in the interval from 0.53 to 1.27. So likewise, if we wanted to say, well, is 0.9 different from 1.2, we also wouldn't be able to reject the null hypothesis there. But if we said, is it different than 1.3, well, then we are outside this interval, okay, and we would be able to reject the null hypothesis and conclude that the coefficient was not equal to 1.3. All right, so using the confidence interval, remember it's always the point estimate, the point estimate plus and minus this quantity based on reliability and variability. Okay, notice that for our test, we were testing whether it was different from 0. We rejected that idea when we did the hypothesis test, and we can also reject that idea by looking at the confidence interval because 0 is not in the interval. Now, another thing we could do is we could go in and we could calculate a predicted y value. That is the response variable or the dependent variable called the y variable. Okay, if we have the estimated regression equation, okay, and well, what we know is we're given the slope coefficient from our estimate. We're given the slope coefficient, and if the problem on the exam gives us the estimated value for the independent variable, well, all we have to do is plug that in. So in this case, if you want to know the return on the stock, you're going to take 0.9 times 1.1%, you're going to add in 0.5%, and you're going to get a predicted value of 1.1%. So in this case, if we say, okay, we think the return on the market next period is going to be 1.1%, what's going to be the return on the stock? Well, we're going to get 1.5% as our answer. That is the predicted value of y given the x input. Right? So if the actual stock return for the next period was 2.3, then we'd have a residual of 2.3 minus our predicted value of 1.5 or 0.8, and we're going to see some more that has to do with this when we talk about the our ANOVA stuff and as we get towards the end of this reading. All right? So, and of course, the 0.5 and the 0.9 and the 1.1 would all have to be given to us on the exam. Now, we calculated a confidence interval on the coefficient. Then we calculated a predicted y value for the whole equation. Now we're going to be back at another confidence interval, and this confidence interval is going to be a confidence interval for the predicted y value. So it's not exactly the same as the one we talked about a few minutes ago, but it's calculated exactly the same in the sense that we're going to have a point estimate, excuse me. We just calculated the point estimate on the last slide. Then we're going to have a reliability measure and a variability measure. The thing to remember here is that this variability measure, when we're calculating a confidence interval for the predicted y variable, is not something that's easy to calculate. The formula is very complicated, and I would say is something that you're not going to see on the exam. So, and the reason for that is when we're calculating a confidence interval on the coefficient, we have to worry about whether or not our model is accurate. So we've got this one source of error. Here we have two sources of error. One, we have the error in the model, okay, that we estimated, but we also have the error inherent in our estimate of the x variable next period. That is the 1.1%. So here we have two sources of error. So we need not the standard error of the coefficient, but we need the standard error of the forecast. What does that mean for you? Well, probably nothing in my estimation, but if it comes up on the exam, they're going to give you the standard error of the forecast. You could have to look up the t statistic, and you could have to come up with the predicted y variable, but all you have to do is put it into the confidence interval, and that is the point estimate plus or minus this quantity that's based on reliability and variability, just like we've seen previously. So looking at an example, 95% confidence interval for the predicted stock return when the market was 1.1%, okay, assuming the standard error of the forecast is 7.8%. Okay, well, we have this 2.2 is our critical t-value. Here is the standard error of the forecast. We're going to find that quantity. We're going to add it to 1.5 and get 3.2. We're going to subtract it from 1.5 and get minus 0.2. So the confidence interval on the predicted y is from minus 0.2 to 3.2. This is not a good place to get bogged down. So it could show up on the exam, could be a question, but it's certainly your fate on the exam is not going to be determined by this particular variable or this particular formula. So a secondary formula sheet would be my thoughts. All right, now let's turn our attention to ANOVA, which stands for Analysis of Variance. I think that by and large, candidates at the level 2 exam overestimate what is going to be involved in ANOVA. All right, so this is a relatively easy thing to deal with if you get the basic concept down, and then if you like Sudoku or whatever that's called, playing those little games or Rubik's Cubes or those types of things, or crossword puzzles, all you have to be able to do is put the puzzle together, and then we're going to see that there's three things we can do with ANOVA in the curriculum. All right, so here's the point. if we could get rid of some of the stuff on this picture, so something like get rid of that for a moment, and what you see here is a scatter diagram. Here we have the if I get this right, okay, we have the line of best fit, right? Well, look, and what we see here is that if this is the mean, if we were calculating the variance and we wanted to look at this observation, all right, so right here, if we wanted to compare it to the mean, we'd say, well, this one was that much greater than the mean, right? But once we use the regression equation, we explain some of the variability. In fact, using the regression equation, we say, well, that the error is only from here to here, right? That's the vertical distance between the point and the line. The point of that is simply to say, let me get rid of some of this, that if we look at an observation, we can see that whoops, let me change tools there, sorry. We can see that this is the total error. So that is the variance, if you want to think of it that way. That's what we call SST, the sum of squares for the total distance from the average. Okay, then we also can come in and see that this is the part of the variation that we explain. So we would expect the prediction here would tell us that the value, if x is out here, that y should be here, right? So this is what we're going to call RSS, the regression sum of squares. And then finally, okay, if I can get one more color here, what about the variability that's up here? Okay, well, we're not able to explain that, right? We're able to explain why it's above average. Okay, so the average would be down here at y. We can explain with the blue part here. The regression equation tells us that it should be up there on the regression line. So that is what we explain, the regression sum of squares. The blue is what we can't explain. So the thing to remember, if that doesn't resonate with you, is that all we're doing is we're taking the total variability. Of course, we're not doing this for an individual observation. We're doing it for all the observations. We're going to take the total sum of squares, and we're going to break it down into two parts. That can be explained, the regression sum of squares, and that is not explained, the sum of square errors. All right? So keep that in mind. So all we're saying here is that the total variability, SST, is equal to RSS, the regression sum of squares, plus the sum of square errors, which is just breaking total variability down to two parts, what's explained and what is not explained. A couple of variables here. K is going to be the number of independent variables. That's going to be easy for what we're doing right now because K is always going to be 1. We're doing simple linear regression. The definition of simple linear regression is that K is equal to 1. We have one independent variable. We're trying to explain housing starts, and we're looking at that in terms of interest rates. And N is sample size. Okay? And if you do that, then you can do several things with the ANOVA equation. So here, and we're going to see in a moment the ANOVA table, and I feel like this slide puts the cart before the horse just a little bit. But what we're going to be able to do is we're going to take this regression sum of squares, and we're going to divide it by K, and that's going to give us MSR, the mean square regression. Okay, we're going to take SSE, we're going to divide it by N minus K minus 1, and that's going to give us the mean square error. Okay? And, well, what does that mean? What's the mean square error and the mean square regression? My suggestion is that you just view those as interim steps in calculating some other things. So what we're going to see is that there's going to be three things before we're done with this reading and the next reading, or this topic summary and the next topic review, where there's going to be three things that we can calculate given the ANOVA table. All right? And these are going to be interim steps. So let's take a look at the table. So looking at this, we're saying, okay, the point here is, and this is a ANOVA table, it doesn't matter if we have one independent variable or 100 independent variables. All we're able to do is saying, here's what we can explain and here's what we can't explain. Remember, as you're looking at this, and this is the Sudoku part, that this first column sums vertically. Okay, so 1 plus n minus 2 is equal to n minus 1, right? So 1 plus n minus 2, and so anyway, n minus 1. Also remember that what is explained by the regression equation plus what is not explained by the regression equation has to equal the total sum of squares, right? So, and then we're going to come across this way to calculate MSR. We're going to take the regression sum of squares, divide it by K, or the degrees of freedom. We're going to take SEE and divide it by this, n minus 2 or n minus K minus 1, however you want to define that, to get MSE. Once we have that, we can use MSR, and we can use MSE, and we can use RSS, and we can use SST, and we can calculate some diagnostics associated with the regression equation. So here we're talking about how to do it. We'll talk about the interpretation and the calculation of what we really want to know after we know how what to do with the table. So let's review. What you have to be able to do is, given some data, we want you to fill in the ANOVA table. Once you fill in the ANOVA table, you're going to know things like the RSS and the SST and the MSE. You can use those variables to calculate something that is going to have some economic meaning or some meaning for the statistical inference that we're trying to make. All right? So in this case, we're going to go back and look at our example. We had 1, K is equal to 1. That's our degrees of freedom. Okay, RSS turned out to be 17.3. If you take 17.3 and divide it by 1, what do you get? Well, you get 17.3. Okay, what if you take the n minus 2 is going to be equal to 10. So we had 12 observations. We talked about that earlier. Okay, the SSE is equal to 5.7. If you take 5.7 and divide it by 10, then you get 0.57. Here we've rounded it to 0.6. Remember, these sum vertically, so 1 plus 10, okay, is equal to what? Well, that's going to be equal to 11. 17.3 plus 5.7 is going to be equal to the total sum of squares. So what we're going to see here is that n minus 1 is 11, okay, and the total sum of squares, SST, is equal to 23. So what are we going to do with that? Well, again, there's 3 things we can do with it. We can look at a couple of those here. We'll see another one when we get into the next reading. Okay, so anyway, looking at this, we can see first that we can calculate the SEE. Okay, so calculating the SEE, okay, that's going to tell us how, this is a measure of goodness of fit, and it's going to tell us how close the dots fit to the line. Now, I don't like to do this much, but I'm going to jump forward a couple of slides and then come back to talk about the calculation here so that we understand what SEE is. All right, so I'm going to jump forward a couple of slides here. Well, let's see, here we go. So what we see here is if we had a regression line that looked like this, okay, then, and we might have that now. So, well, I guess I could just use the line that was already there. So what you see here is a regression line, but look how far the dots are from the line. So we've got the dots a long way from the line. What we're going to see is that gives us a high SEE. SEE stands for standard error of the estimate. Don't confuse that with SSE, which would be the sum of squared errors. So you got to keep your SEE straight from your SSE in order to do this. I realize that's a lot of S's and E's, right? Anyway, the point is, here, the dots are a long way from the line. You can think of this as a variability number. Okay, so we end up with the dots a long way from the line. However, with the exact same slope, we could see an equation that looked like this. Well, now the dots are all very close to the line. That's going to give us a low SEE. All right, now let's go back to the calculation of SEE just so we can see that real quick. We'll get another look at this, by the way, in the next